held on like poles will attract each other. And that's it. So the next question is, how do charges behave inside a magnetic field? What do they do? All right, so the physicists decided to conduct a bunch of experiments trying to figure out what happens to charges. All right, so they set up a magnetic field, and that's exactly what we'll do. So the magnetic field is pointing from left to right, a constant magnetic field that we're looking at. And then we will just drop charges into this field. All right, so the first case is they will place a static charge. All right, so this charge is going to be static, so it's not moving. All right, so no motion involved. So the result of the experiment is nothing happens. Nothing. All right, so place the charge inside a magnetic field. It's a static charge, it doesn't move, nothing happens. The next experiment, have the charge move along the direction of the magnetic field. So have it move parallel to the magnetic field. Check to see if it speeds up, slows down, or changes direction. Once again, nothing, nada, nothing happens. The third experiment, well, this time just send the charge across the magnetic field. And then check to see what happens. As soon as you send the charge across the magnetic field, something weird happens. Charge becomes deflected. You end up getting a deflection in a direction which is 90 degrees to this motion. So this is moving in this direction. And then what's happening is it's going to experience a force, 90 degrees to this motion. All of a sudden it gets deflected by this force. This is known as a magnetic force. All right, so this is weird because there's a force acting on it, but the force is not along the direction of the magnetic field. The force acting on it is 90 degrees to this motion. It's causing a deflection. The obvious question is why? And that's the right question to ask, but unfortunately we don't know the answer to that question. So only thing we can do with it is just formalize the observation in the mathematical form. So what's happening is if the charge is going across the magnetic field, it's going to become deflected, which means that it's going to experience a force. It's going to be 90 degrees to this motion. And that's it. So that's what happens. So charges at rest will not experience a force. 90 degrees to the velocity vector or the magnetic field line. It's got to be 90 degrees to, okay, I always look at the direction of the force in terms of, and I'll say 90 degrees to this motion. It's also going to be 90 degrees to the magnetic field line, but ignore that one. It's got to be 90 degrees to this motion. All right, so if the charge is at rest, okay, nothing happens. The charge is not moving parallel to the magnetic field lines, nothing happens. As soon as the charge starts to go across the magnetic field, all right, so it's moving across the magnetic field in this direction, it's going to experience deflection because there's going to be a force acting on it, which is going to be 90 degrees to this motion. Okay, why am I focusing on the fact that it's 90 degrees to this motion as opposed to the magnetic field? Okay, it'll become fairly obvious from a conceptual perspective because it's going to help you understand it better somehow because something happens. All right, so the direction of the magnetic force is determined by something called the right-hand rule. There are two right-hand rules we will get to use. Okay, so I will call the first one the right-hand rule number 1. The second one, I will call it the right-hand rule number 2. Okay, so these rule number 1 and rule number 2 are the rules that I myself named. In the books, they just call them right-hand rules, depending upon the applications. I'm going to refer to them as right-hand rule number 1 and right-hand rule number 2. All right, these rules come out of calculus. There are different ways of interpreting it. The one that I use is this one. Okay, from calculus, this is from Calc 3. This is called cross product, so let's just wait on that one. Let's use something a little bit more intuitive. All right, so the right-hand rule, the way I will apply it is going to go like this. Number 1, you have to use your right hand. Number 2, the right hand usually works for a positive charge. For a negative charge, switch to your left hand. If it's a positive charge, stick with the right hand. So the right-hand rule is applicable to positive charges. All right, so this is the direction that the charge is moving. So line up your thumb in the direction of the velocity vector. Fingers will be lined up in the direction of the magnetic field, and palm is going to open up in the direction of the magnetic force. All right, so you have to use your right hand. So the thumb is going to be in the direction of the velocity vector. Fingers will point in the direction of the magnetic field, and palm, there's going to be a vector obviously coming out of your palm. This is going to be the force vector. All right, so your palm opens or points or faces in the direction of the magnetic force. All right, so okay, so I spent enough time going blah blah blah, so let's talk about the right hand rule number 1. All right, so right hand rule number 1. All right, so we will just RHR number 1, right hand rule number 1. They mean the same thing. All right, I messed it up. All right, so it goes like this. Number one, you have to use it for a positive charge, 0 positive charge, and the magnetic field from left to right in this case. And the charge is going across the magnetic field in this direction. So it's got velocity. All right, so let's make sure that these are vectors, so clearly denoted. And then, all right, so line up your thumb in the direction of the velocity vector. Fingers lined up in the direction of the magnetic field. And then the force is going to be in the direction of your palm. So your palm is going to face in the upper direction. Okay, so that's it. And for reasons that will become obvious, let's place an angle right here. Okay, just for now. I don't want to use any mathematics right now. We'll turn this into an equation at some point. Until then, let's get a conceptual understanding. All right, so your thumb is in the direction of the velocity vector. You line up your fingers in the direction of the magnetic field. Your palm is going to open in the direction of the magnetic force. Okay, so this is a 3-dimensional representation. Okay, and then what I'm going to do is we will do some kind of a conceptual exercise. All right, so that you guys can actually visualize this. All right, the notation that I'm going to use, I'm not sure if you guys use anything like this in Physics 1 as yet. If a vector is coming out of the page, all right, if it's coming out of the page, this is the notation that we will get to use. If the vector is going into the page, this is the notation that we will use. So we are using 2-dimensional, all right, so 2D representations. All right, so 2D representations for vectors. All right, so arrow is coming out of the page, the arrow is going into the page. All right, so the magnetic field in this case is going to be going into the page. I'm going to space them equally within this region. So this is a constant magnetic field region. All right, so and then what I'm going to do is I'm going to project a positive charge into this region. All right, so I'm going to have the charge come in. All right, from, okay, let's just have a charge. Let's place the charge right here. And this is a positive charge. Okay, so I'm going to project the charge in this direction, and then I'm going to check to see what happens to the charge. All right, so the magnetic field is going into the page, and the charge is projected in this direction. All right, so charge is projected in this direction. All right, so what you need to do now is you have to use the right-hand rule. Okay, line up your thumb in this direction. All right, so your thumb is pointing in this direction, and then your fingers are going into the page. Okay, thumb is in this direction, fingers are going into the page. Immediately you will notice that your palm is facing this way. All right, so which means that there's going to be a force acting on it, and this force is going to be 90 degrees this motion. So there's a force acting on it. So what does this force do? Guys, what does this force do? If the force is 90 degrees this motion, it's going to cause it to actually turn. All right, so it's going to change its trajectory. All right, so which means that at some point the charge is going to be here, and at that point it's going to be moving to the right. And once again, you have to use the right-hand rule. All right, so line up your thumb in this direction, your fingers are going into the page, and there's going to be a force acting on it. This force is going to be 90 degrees this motion. Again, boom. So what's happening is, all of a sudden, notice that this thing just, ooh. All right, this is more like it. It ends up curving. All right, so because the force is 90 degrees this motion, all right, it's going to keep yanking it in this direction. So at some point, this charge is going to be here somewhere. It's going to be right there. All right, so I'm going to place the charge right there. This time, the charge is moving in the upward direction. It's got a velocity vector. So once again, it's the same game. Thumb is in this direction, the fingers are going into the page. Thumb is in this direction, the fingers are going into the page. So there's going to be a force acting on it. So once again, the force is going to be to the left. And because the force is 90 degrees to the motion of this charge, it's just going to do this. Okay, so once again, it's going to curve in that fashion. All right, so going back, the force is 90 degrees to the motion, so it's going to keep yanking it in this direction. So at some point, the charge is going to be here, moving in this direction. And I think at this point, it's fairly obvious what's going to happen. All right. I mean, even if you're a Republican, I think at this point, you can see the big picture, guys. All right. It turns into a circular motion at this point. Boom, 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 boom. So what's happening is boom, boom, boom. And the force is 90 degrees this motion. If the force is 90 degrees this motion, this is known as a centripetal force. That's the reason why when I said, oh, it's going to experience the force 90 degrees this motion, immediately when somebody says that, I know we're talking about circular motion. All right, so what that means is the magnetic field interacting with the charged particle is going to cause it to wrap around the magnetic field. So that's what it does. All right, boom, boom. So you end up getting circular motion. And this magnetic force becomes the centripetal force as a result. So what that means is, three-dimensionally, what that means is, when you have a magnetic field like this, and when you have a charged particle coming in, it's moving in this direction. So when the charged particle starts to go across the magnetic field, it's going to experience a force 90 degrees this motion. So it just wraps itself around the magnetic field. That's what it means. Okay. In that way, the magnetic field is able to trap this charged particle. So the charge going across the magnetic field is going to get deflected at 90 degrees this motion, so which means that the charge is going to get wrapped around the magnetic field. All right, so that's what the Earth's magnetic field does in essence. If the charged particles going across the magnetic field, they will become trapped by the magnetic field. All right, so incoming charged particles will get trapped by the magnetic field, and then they will get driven into the atmosphere, colliding with the air molecules, exciting the air molecules, and as a result, what happens? It's going to cause the northern as well as the southern lights. Okay, so these charges colliding with the air molecules will cause the molecules to become excited, so the electrons end up jumping inside these molecules, generating light in essence. All right, so Earth's magnetic field will only protect us from these charged particles. All right, pick and choose the best answer. Whenever you guys are ready, just jump in.
B.
All right, so the best answer is going to be B. Okay, so only when the charges are going across the magnetic field will they'll experience a force. Give yourselves 5 points for one. All right, just work this out. You may have to draw something.
C.
Okay, so C is the best answer, right? Particle, give yourself 5 points. Those of you guys who pick C, give yourself 2 points. If the charge is moving parallel to the magnetic field, they will not experience a force. All right, so whenever you're ready.
C as well.
Okay, so charges stationary, so no force acting on them. So those of you guys who said C, give yourselves 5 points. Those of you guys who pick C, give yourself 2. Answer. Okay. Okay, so study this. Take all the time you need. I'll give you guys 1 more second. Time's up. Only question I have is the shape, guys. What is the shape remind you of? Okay, so fluid dynamics. How many of you guys studied fluid dynamics in Physics 1? All right, so this is known as the constancy of the mass flow rate. So when you force the fluid into a small opening, like the water coming out of a partially closed hose, what happens? Yeah, it goes up, right? This is just going to speed up. The same thing, the propulsion unit. So you got this bottleneck shape. So the fluid goes in, and then you got the propulsion unit here, and then when you force the fluid into a small opening, it's simply going to speed up. That's what it is. So it's going to accelerate, which means that the action force is going to be acting on the seawater in this case, and the reaction force is going to act on the propulsion unit. So that's physics. That's Physics 1. So let's move on to Physics 2. All right. Physics of the propulsion unit is straightforward. You got this capacitor. These are huge mass capacitors. Okay, so this is positive charge, this is negative charge. And then you generate a current moving in this direction. So the positive charges are moving in this direction under a very strong magnetic field. So what happens, they will experience a deflection 90 degrees to their motion. So the charges will become deflected in this direction while taking the fluid with them. All right, so physics of it is straightforward. The engineering of it is far more complicated for the obvious reasons. Okay, so you end up causing a deflection into the smaller opening while hoping that the charged particles, somehow will be able to push the water molecules in the same direction into your smaller opening. All right, so that's the least of your problem. Okay, so how much current you need to generate? How strong does the magnetic field need to be? This sort of stuff is really, really difficult to figure out from an engineering perspective. Conceptual physics is straightforward, but the engineering is fairly complicated. And it's supposedly we have this technology today. As far as I know, obviously it's top secret. So they can make themselves sonar invisible. evidently.